If you've ever been to a place where the ground looks like this, or been in a building that looks like this or this, there's a good chance you were in a place that had expansive soils. Just like these dinosaur toys, certain types of clay soils change their volume depending on moisture content. They swell when they get wet and shrink as they dry. This is a microscopic mechanism where the shape and arrangement of the molecules actually change according to the amount of water mixed in. And large portions of the US Gulf Coast and Great Plains have these kinds of soils. If you're starting a foundation repair or road paving business, this is an important map for one very good reason. Expansive soils break stuff. Movement on its own, and especially very slow movement, is usually not a problem for structures. This is why we can lift buildings and even move them to new locations. What causes damage is differential movement. This is where certain parts of a structure move relative to each other. Differential movement leads to sticking doors and windows, cracked walls, and just general out-of-plumbness. And this is why expansive soils are so insidious, because they don't expand and contract evenly. For example, if your house sits on a concrete slab and you haven't had any rain, the soils around the edges of the slab will dry out and shrink while the interior remains moist. Now you get a foundation with no support around the edges. And this breaks one of the fundamental laws of civil engineering, which says, and I quote, "You gotta have dirt underneath your concrete." Expansive clay isn't just an issue for buildings. All kinds of infrastructure are at risk of damage from a shifting foundation. Leaking pipes can cause swelling of the soil, pulling apart joints, and eventually leading to issues like sinkholes. Rainwater infiltrating through the cracks in roadways causes localized areas of swelling, making the road bumpy and uneven. Not even sidewalks, and by proxy rollerbladers, are spared. When designing to account for expansive clays, engineers not only have to know how much the soil can change in volume, but also how hard it can push on anything sitting above, also known as swell pressure. So I've rigged up a little test so that we can see not only how soil swells, but also how much pressure it can exert. This apparatus is called an odometer, and it's similar to a hydraulic cylinder, except I'm using dirt instead of oil. I'll use a dial indicator to measure how far the sample is able to move the piston. If you work in a soil laboratory, I'll just apologize now for the rest of this video. For my first test, I've got some soil straight from my own backyard. After all, there's no place like a geologic unit containing abundant clay with high swelling potential. I put this in the oven to dry out first. Let's put it in the apparatus and watch what happens. As it saturates, the soil expands over time, eventually reaching a 10% increase in volume over its dry state. Trust me, that's enough to put a crack in the drywall. But it's really not that dramatic on video. So to help illustrate the rest of these concepts a little better, I've got a bag of instant viral video. That's right, I'm talking about super absorbent polymer beads, also known as Orbeez. These beads actually behave very similar to expansive soils, except they're way cooler than dirt in almost every way, even for a civil engineer. First, I tested these with no confining pressure, and went a bit overboard. You can imagine if you built a house on this, you might get motion sickness every time it rains. It would wreak havoc on your structure. I tried it again with fewer Orbeez, but it was still too much. This is an exaggerated view of what happens as water penetrates the subsurface and saturates an expansive soil. It's hard to imagine anything that could avoid damage in this environment. So let's add some weight, and fewer Orbeez this time so I don't max out the range of my dial indicator. You can see that these fishing weights hardly make a difference. And that makes sense, right? A house probably puts more pressure on the ground below it than a few fishing weights. What about 10 times that weight? It takes them a bit longer, but these Orbeez are still able to swell to their full dimension under this 20-pound barbell, which is about the most my little acrylic odometer can handle. This is not just the case for Orbeez, by the way. Some clay soils have swell pressures on the order of megapascals. That's hundreds of pounds per square inch. So you can see how big of a challenge these expansive soils can pose. there are lots of ways that engineers try to mitigate damage from these kinds of soils. You can simply remove all the expansive clay and bring in better soils for your project. You can grade the site so that water drains away from the structure, keeping moisture fluctuations down. You can mix chemicals into the soil that limit its ability to absorb water. Finally, you can simply build heavy enough to counteract the swell pressure and keep the soil from expanding. But as we saw in the demonstration, even a small amount of soil, or in this case a colorful soil surrogate, can lift a lot of weight. I'm leaving out the simplest solution, of course, which is simply to avoid expansive soils altogether. But that's generally not feasible. It may be true in the parable that the wise man built his house on rock, but some civil engineer had to build a road to that guy's house, and the engineer didn't get to choose what kind of soil was on the way. Expansive soils are not a particularly newsworthy or exciting hazard, unless you're the type of person who makes videos about dirt in your garage, but they still cause a tremendous amount of damage to buildings and the public infrastructure that we rely on every day. They are one of the many factors taken into account when designing civil structures and the subject of ongoing research to find cost-effective and sustainable practices for mitigating the damage they cause. Thank you for watching, and let me know what you think.